Good morning, students. Audio is okay.
Yes, sir.
So, welcome in next lecture of Math F242 Operation Research. Presently, we are studying basic element of the queuing system or queuing theory. So, we have seen basic. There are the few basic elements, and we have discussed uh, means population of the prospective customers, then arrival pattern, right? Then queue discipline or service discipline, service mechanism. Now, next is the probability distribution, probability distribution of the customer service time. So here, customer service time is what? It is the random. Means for one customer, a server may take 1 minute, or for another customer, he may take for 10 minutes. So this is the random variable. Since it is the continuous, so we can say it is the continuous random variable. And if it is a continuous random variable, then it is characterized by some PDF or CDF. So let's say it is the FT or FT. So that's we have. So the service time for different customer will be assumed to be independent random variable having a common probability distribution. This distribution can be approximated by actual observation. If it is not is any standard one, then you can approximate by observing how many customers you are serving, right, in a particular time interval. With that you can judge. So from there, if you say that mean service rate of the server if constant will be denoted by the mu is what? It is the mean service rate. Mean service rate. So mean service rate means on an average how many customers the server has served in a unit time. In a unit time, right? So this is the number of customer that can be served by a single busy server in an unit time. Means if it is the unit time, if it is the unit time, so how many we have the different customers, right? We are serving the different number of customers. So on an average, how many customers we have served in a unit time, that we denote by the mu. So it is mu is nothing. Mu is the expectation of the random variable. It is the et, it is the expectation of the random variable. And we know that what is the formula of the expectation. It is the, because continuous random variable, so random value into associated probability distribution. So t into ft, right? So actually not this, 1 upon this, right? Because if mu is the service rate, 1 upon mu will be the mean service time. 1 upon mu will be the mean service time. Mean service time. And service time is the random variable, so it is equal to t ft into dt. T into t ft dt, value into probability. So here it is written, consequently mean service time would be 1 upon mu, and 1 upon mu is nothing, right? If a service facility has s servers, then we would assume that each server has the same mean service rate, or it may be the different. So what is the meaning of this? If the multi server have the same mean service rate, then we say that is the homogeneous system. That is the homogeneous system. If it is different, then we say it is the heterogeneous system, right? Heterogeneous system. So we may have either the homogeneous system when all the servers, if there are s servers and all servers have the same mean service rate, then we say homogeneous system, otherwise heterogeneous system. So here, so just I am playing one video for you. My new video, new screen is visible.
Yes, sir.
So this is the actual service system we have. So here you can observe the server is providing the service, and here the customer are getting the. So now presently the it is showing the impatience behavior of the customer, right? That we have discussed. It is the jockeying behavior. He is joining the adjacent, right, adjacent queue, because he is feeling that adjacent server is providing the service with faster rate. So presently server is on vacation, right? One server is on vacation. He is not. He was not present at that moment. Right. So now both server has have gone, right? So means sometimes it is not necessary that whatever the means you are thinking always correct, or everything is unpredictable in nature. Now come to this screen. So means depending over the situation, we can have different type of the queuing system. So how we can judge whether the system is performing correctly or not? So for that purpose, we have to define the state of the system, right? We have to define the state of the system. So in general, in the state of the system, what we can notice as a customer, how many customers are there, whether the server is working or not, whether he is on leave, he is on vacation, right? So all these things, and what is the service capacity, all these things we can observe. So that come under the state of the system. The state of the system at a given instant refers to number of customer in the system, means at the particular time, at the particular instant, means at the particular time t, that refer as a number of customer in the system, right? Always we call as a in the system. So in the system we have those customer, it includes those customer who are in service plus those customer who are in queue. So system at a given instant, which include those who are under service plus those who are in queue. So this we say that it is the n, right? Number of customer in the system we denote by the n, or you can say it is the observed value. It is the observed value at the particular time. So at the different t, we have the different value of the n. So it is the random in nature. Number of customer is random in nature. So it is what? It is the random variable. Random variable, or you can say it is the discrete random variable. Discrete random variable, it means if it is a random variable characterized by the point probability function or the probability mass function, let's say it is the PNT. PNT means it denote the probability. It denote that probability at the particular time, at the particular instant, there are n customers. At the particular instant, there are n customer, or at the instant t there are n customer. So it denote the by the pnt. Now this pnt, from this pnt we can compute other performance measures also. So main important here, state of the system denote how many customer we have at the particular instant. During the transition, during the transition, the state of the system may have the probability distribution which will be time dependent. So presently, whatever I have written that P and T, it means it is the time dependent. So that type of the analysis is known as the transient analysis. Means time transient. We say that transient probability. So PNT or time dependent analysis. So probability distribution which will be time dependent. Given time dependent, given the is given the state at t. But in the long run, when we have the long run, in the long run we have stabilized. We have stabilized the system, right? That is means after the infinite time. After the infinite time, as the limit t tends to infinity, after the infinite time, this pnt will become the pn. Now it is independent of, right? This pnt will become the pn. Now this uh, probability probability is independent of the time. So this pn is known as the steady probability, steady state probability. This pn is known as steady state probability, right? This is the steady state probability. So steady state pn denote probability that there are n customer in the system. Pnt denote there are probability that there are n customers in the system at time t. That is only the difference. Means here we can have the two type of the analysis, either the transient analysis or the steady state analysis, that is depend over the time or independent of the time respectively. Means in general, when we have the long run system, we prefer to do the steady state analysis. When it is the developing system, then we prefer the transient analysis. And in the system, in the system we can have the either the zero customer or the one customer or the two customer or the three customer. Means when we say p and t, right? P and t, so here n can be either the 0, 1, 2, 3, right? And t is greater than 0, or pn for n is equal to 0, 1, 2, 3, and so on. So first one is the transient state probability, second one is the steady state probability. Now these probabilities can be used to find the mean number of customer in the system or mean waiting time of the customer in the system or in the queue. Since we have now the associated probability, so from here we can determine different type of the performance indices. So in this most important performance indices is how much I have to wait. So on an average, how much I have to wait, how much any customer has to wait, or right, how many on an average how many customers are there. So that we have to determine. So here L denote average number of customers in the system, right? This denote mean number of mean number of customers in the system, mean number of customer in the system, right? LQ denote mean number of customers in the queue. In the queue, W denote expected waiting time. Expected waiting time. How much I have to wait? Expected waiting time in the system. Expected waiting time in the system. And WQ denote expected waiting time in the queue. Right? Means when we are saying that in the queue, totally in the line. When we say in the system, that is the in the queue plus in service, because service also takes some time. Service also takes some time. So that will denote the waiting time in the system or expected number of customer in the system. So that we can determine from the is from the state probabilities, either the transient state probability or the steady state probabilities. So sometimes the state of the system and affects the mean arrival rate of the customer or mean service rate of overall service facility of the system. In such cases, the rates are denoted by the lambda n and mu n. See, whenever we have the more customers in the system, means that is the state. Whenever we have the more number of customers in the system, let's say state, right, n. So with that, what will happen? The customers show the reluctance behavior to join the system. Means rate will decrease. Rate will decrease. If there are less customers, more customer will join. Means rate will increase. So you can say that lambda arrival rate depend over the number of customers. Depend over the number of customers. Similarly, if there are few customers, server will provide the service with slow rate. But if there are more customers, right? If there are greater number of the customers, then the server will provide the service with faster rate. So that is the, if the mu denote the service rate of the server, and it depend over the number of customer in the system, that is the mu n. So these type of the rates are known as the state dependent rates. State dependent rates. State dependent arrival rate or state dependent service rate. That's why state is very important. State define the system, as well as from that we can judge whether the system is performing effectively or not, whether the our system is efficient or not. So now I'm saying that we have the multiple system. So how we can recognize the queuing system, whether which system we are talking? For that we have the candle notation, right? We have the candle notation. So candle notation we denote by the A B C D E F, right? Candle notation we denote by the A B C, right, D E F, where F denote, right, F denote the population size. F denote population size. How much population for means what is the limit of the population? Generally we denote it by the K. Generally we denote it by the K. It may be finite. It may be the finite or infinite. It may be the finite or infinite. Then this denote the system capacity. System capacity means how much customer the system can accommodate. Generally we denote it by the small m, right? It may be finite or infinite. It may be finite or infinite. Then D denote the service discipline. D denote service discipline. Service discipline. It may be FCFS. It may be last in first out. It may be service in random order. Service in random order. It may be some priorities, right? Some priorities or many more. Then this C denote number of servers. This C denote number of servers in parallel. In parallel. So generally we denote it by the small s. Then here we have, it denote the probability distribution. Probability distribution of service time. Probability distribution of service time. And this denote the probability distribution of distribution of inter arrival time. Inter, instead of the arrival, we write the inter arrival times because continuous random variable. Inter arrival time. So these two may be capital M. Capital M denote the Markovian, right? Capital M denote the Markovian. For here we have, so here A and B can be the capital M, means when the inter arrival times or the service time are independent, identically distributed, and they are the exponentially distributed. Exponentially distributed. For the exponentially distributed, we have one important property known as the memoryless property. Known as memoryless property. During the exponential distribution, I have told you this memoryless property. So, due to the memoryless property, or this memoryless property also known as the Markovian property. Markovian property. Markovian property. So, due to this property, we denote the exponential distribution by the capital M. D, if we have the inter-arrival time or service time as a deterministic, we know that after every 10 minutes, after every 5 minutes, one customer will come, right? That is that fixed time, certain time, deterministic. If we have inter-arrival time or the Erlangen, Erlangen is the special case of the gamma distribution, right? When we have the arrival or departure in phases. Whenever we provide the service in phases, means first phase take the few time interval, second phase take the few time interval, third phase take the few time interval, and all these times are independent to each other and follow the exponential distribution, then we say it is the Erlangen, right? It is a special case of the gamma distribution. I am saying that let us we are providing the service in phases. Let's say first phase complete, then second phase complete, then third phase complete. So here you can say it is taking the T1, it is taking T2, it is taking the time T3. So all are random variable, random variable, and characterized by the exponential distribution, right? So then we say the total service time or inter-arrival time follow the Erlangen distribution, right, with phase 3. Means in that case, that will be the E3. EK means in K phases. So E3, Erlangen. Then means it is not necessary always these distribution are standard. It may be the journal, right? It may be arbitrary anytime, any distribution. So that we denote by the GI or G. We prefer for the interval time, and G for the, right, G for the service time. So interval time or service time are governed by the some journal distribution. So that we denote by the G. Any doubt to understand this? Anything you want to repeat? I have told you D denote the Q discipline or the service discipline. It may be first come first out, last come first served, service in random order, or any general Q discipline. For example, if we have this MM1 FCFS 2050, what it means? Anyone please try what it means? Anyone please try what this M denote? It denote
Both
inter. Yes, yes, please.
both service and interval time both are exponentially distributed, and there is one
Yes,
server who's working. So it's the
one server is working. Huh?
first come first serve is the service discipline, and the capacity is of 20, and the population which has to be served is 50.
Right. So with this candle notation, you can recognize which queuing system we are talking. Right. So that is the candle notation. Now, throughout the chapter, we will use the following notations. Some notations already you know, some notation we will define. So here, terminology and notation. So what is the NT, N or N? What it denote? I have already discussed.
Number of customers.
Number of customer in the system. Just not a number of customer. Number of customers in the system. So NT means time dependent, N means time independent, steady state, and this small n denote the first first capital are the random variable. Random variable, since it is the number of customer, right? So it is the discrete random variable. Discrete random variable, and small n denote the observed value. Observed value of the that number of customers. So it number of customers in the system. So it denote that number of customers in the system. What is the QTQQ? Now I think you can judge. If n
Number
denote the
of
number of
customer in
customer
the
in the
queue.
system, so it denote the number of customers in the
Q.
queue, right? In the queue. And U denote UTUU, right? It denote the number of customer in service. Number of customer in service. It means from here we can say that n is what? N is the q plus u. N is q plus u. Then PNT. What is the PNT? Probability that there are n customers in the system when it is the PN steady state, or PNT means at time t, that is the transient. If it is the t, then the transient. If without t, then the steady state. What is the S and M? S denote number of servers in parallel. Number of servers in parallel. And M denote system capacity. System capacity. System capacity. What is the L? L is the expect. L is the expected. What is the L? L is expected number of customers in the system, right? Expected number of customer in the system. When we say expected, means it is the E or of the random variable n, right? It is the expectation of the random variable. It is the expectation of random variable. So we denote it by the En. What is the LQ? It is expected number of customers in the queue. That is the E of Q. And what is the formula of the En or any expectation? N is which type of the random variable? N is which type of the random variable? N is which type of the random variable? Yes, discrete. One has answered, it is the discrete. So due to the discrete, we have the summation, right? Summation of what? Value into probability, that is the Pn into associated probability Pnt in case of the transient, otherwise the Pl in case of the steady state. And number of the customer in the system may be 0, maybe 1, maybe 2, maybe infinite. So summation n is equal to 0 to infinity npn. Npn. That is the En, EQ. Clear this part? If I say Ts is waiting time, Ts is waiting time in the system. In the system, TQ is, or instead of the T, let's say it's capital T only. TQ is waiting time in the queue, and TS is the waiting time in service. Waiting time in service. Right? Waiting time in service. So, which type of the random variable it is? It may be, it is a random variable. So, which kind of the random variable it is? Yes, it is the continuous random variable. It is the continuous random variable. So continuous random variable means mainly it is characterized by the some PDF, CDF, and we can compute their expectation. So if you compute the expectation, right, ET means expected waiting time. Expected waiting time, right? Expected waiting time in the system. Expected waiting time in the system. So that we denote by the capital W. Similarly, E of TQ, expected waiting time in the Q, we denote it by the WQ. We denote it by the WQ. So here we have the those notation L, En, LQ, EQ, right? Means L is equal to En, LQ is equal to EQ, expected number of customer in the system, expected number of customer in the queue respectively. Then W and WQ, expected waiting time in the system, expected waiting time in the queue. So what are the relation between these two expectation? For any queuing system in which steady state distribution exists, if we are talking only for the steady state, not for the transient, steady state exists, the following relation hold. L is equal to lambda into W, where L is what? L is what? Expected number of customer in the system. W is what? Expected waiting time. And lambda is what? Mean arrival rate. Mean arrival rate. And LQ is equal to lambda into WQ. That is expected number of customer in the queue, mean arrival rate, expected waiting time in the queue. LS is equal to lambda WS, that is number of customer in the in service into a mean arrival rate, waiting time, expected waiting time in service. And all this is known as, all these formula are known as the little formula, right? They are known as the little formula. And these formula, right, these formulas do not holds for the lost customer. If there are some lost due to the impatience, due to the limited capacity, due to the limited population, then these formula will not hold. If there are some losses of the customer, means if we some customers are not getting the service, some prospective customers are not getting the service due to any reason, then this formula will not hold. This formula will hold only when all intended customer get the service. So, as I have discussed you, first we compute the states, right? State means a number of customer in the system, n. Then it is a random variable, so we compute the corresponding steady state or transient state probability. From there we compute the performance measure. So some performance measure already we have seen, or characteristic of the system, right? So first one is the expected or mean number of customers in the system, that we denote by the L. L is the nothing. L is En. En, and n is what? It is the discrete, so it's summation from n is equal to 0 to infinity of value, right? Value into associated probability. So NPN. Similarly, expected or mean number of customer in the queue, we denote it by the LQ, that is the E of Q, and it is nothing. Now, here the question arises: how let's say we have the four server system. First customer is arriving. What happened? He can go to anyone. It means presently one server is busy. Then there are second customer. He go here. Then the third customer. Then the fourth customer. Right? So expected number of customer in service, expected number of customer in system presently are 4. Clear? Now, if we have the fifth customer, then expected number of customer in system, or means number of customer in the system will be the 5. Number of customer in service is equal to 4, and number of customer in queue will be the 1. Clear? That is the situation. Now, if I have to compute the expected number of customer in queue, EQ, LQ. So, what will be the value? What can be the value? Generally, we have now Q, right? Q and PQ. But here we have not defined anything PQ. Instead of the PQ, we have defined the PN, mean number of customer in the system. So how I can write the Q in terms of the N? How many customer will be in queue if there are
N
n
minus S.
customers in the system? If there are n customer in the system, then how many will be in queue? What you have to subtract? Yes, right? So it is the not m, number of server, not n minus m. It will be the n minus s, number of server in parallel. Number of servers in parallel. So if all the servers are busy, then only there is a queue. Right? When all servers are busy, then only there is a queue. So n minus s, Pn, where n start from s to infinity. Before that, there is no queue. Right? So if you have any doubt, please ask. If anyone has any doubt regarding this formula, please ask. Why I am writing the summation n is equal to s to infinity n minus s Pn. Clear? Then mean if mean effective arrival rate can be defined as mean effective arrival rate means if there are losses, if there are impatience. So exactly how many customers are joining, that we can define as lambda n value into associated probability, right? Mean arrival rate by the lambda, and it is nothing, it is a summation for n is equal to 0 to infinity lambda n pn, where lambda n is what? It is the state dependent state dependent arrival rate, state dependent arrival rate, and into associated probability. Similarly, mean effective departure rate means on an average how many customers are departing from the system. We denote it by the mu var or d var, and it is equal to value summation because number of customers, it is the number of customers, so discrete random variable, so it is the summation n is equal to 1 to infinity mu n into pn, value into probability. What is the mu n? It is the state dependent service rate, state dependent service rate into associated probability. If we are talking for the steady state, if we are talking for the steady state, then always the mean arrival rate is equal to the, or mean effective arrival rate is equal to the mean effective service rate, right? Means the customer who join the system always get the service, right? The customer who join the system always get the service. That is the mean effective arrival rate is equal to mean effective service rate, if we are talking for the long run system. Then from the little formula, using the little formula, we know that W is equal to, or L is equal to lambda into W. So W can be determined as L upon lambda, WQ as a LQ upon lambda Q. And expected number of BG server. How many customers are busy? How many servers are busy? Presently, if I'm talking this, so if there is the first customer, so only one server is busy. If there are the two customers, two servers will be busy. If there are the three customers, then three servers will be busy. If there are four or more customers, then all four servers are busy. So if you have to compute the expected number of busy server, out of the four available server, that we can determine as a lambda var upon mu, and that also denote the expected number of busy server is as same as expected number of customers in service. Expected number of customers in service, both are the same thing. The mean number of busy servers or mean number of customers under service is nothing, EB is equal to lambda var upon mu, where random variable B denotes number of busy server at any instant or number of customers in service at any instant. So what is the relation between, that this relation I will discuss again after the few derivation, right? But here you just note down. Now we have the two expected waiting time and expected waiting time in the system and expected waiting time in the queue. So it is the W is equal to WQ plus 1 upon mu, right? So actually what is the W? W is what? Expectation of waiting time in the system. Waiting time in the system is the random variable, its expectation. What it denote? Expected waiting time in queue. And what is the expected waiting time in the system? that is the expected time of service, right? Service in service. So in service, what is the meaning of the in service? Means mean service time. Mean service mean service time and mean service time in last slides we have seen it is the 1 upon mu. That's why it is the W is equal to WQ plus 1 upon mu. And if in the above relation you multiply the lambda throughout, so lambda into W we know that it is the L, lambda into WQ is known as the lambda Q, and plus lambda upon mu, that is the relation between the expected number of customer in the system and expected number of the customer in the queue. And this we denote by the rho. Lambda upon we denote by the rho, and it is known as the utilization factor. And L can be the how many customers in the queue. Effective arrival rate, right? Effective arrival rate minus effective departure rate into the time so time and time cancel, so that will give you effective number of customer in the system, that is the expected number of customer in the system. So L is equal to lambda var minus mu var into T. Up to the time T, what is the effective arrival rate or what is the effective departure rate? So their difference in that time will give you expected number of customer in the system up to that time T. Right, so that's all for today. From next class I will start the this onward. So today we have discussed the terminology and notations that we use throughout the chapter. If you feel any doubt, please ask. Platform is open. Neil, Nishant, Kunal, Abhinav, is there any doubt? Dipanshu? Yes, Roy, what's the doubt?
Sir, can you repeat the part where you told that it is not Little's formula is not valid for the number of lost customers? I did not get that.
Yes. So it little formula do not hold when there is any type of the lost customer. Lost customer means there is the prospective customer who wants the service from the system, but he is not getting the service due to some reason. Either he left himself, or there is no availability of the server, or maybe any other reason. But he is not getting any service from the system. Then uh, this relation will not hold.
Okay, sir, got it.